So, in our solid state physics laboratory, I will demonstrate Hall effect experiment. As I describe the theory of this experiment, so we will measure the Hall coefficient of N type germanium semiconductor. So, this is our sample. Here you can see this is our sample, rectangular sample, okay, a piece of sample we have taken, and Hall geometry I have shown you, this experimental geometry. So, there will be 4 probe. Okay. So, here you can see these 4 connection we have taken. So, 2 are along this direction, along x direction, and 2 are along y direction, perpendicular direction. So, 1, 2, 3, 4 probes are there. Okay. So, these probes are getting contact, it is on the sample. Okay. So, and these are connected, I think other side I can show you, So, these 4 probes are connected with wires. So, this connection, this side you can see this connection. So, these 4 probes are connected with this wire. So, this wire, 4 wires are coming, and 2 are for applying constant current and 2 are for measuring the Hall voltage. So, this is the basically constant current source and voltmeter, both together it is there. So, here you can see we can display the millivolt and milliampere. So, that means there are millivoltmeter and milliammeter, both are in this box. So, you can choose here, you can see this is the current and this is the voltage. So, if you keep knob this side, this is the current, this if I put the other side, it will show the voltage. Okay. So, 2 out of these 4, 2 are connected with the current and 2 are connected with the voltage. Okay. Means the voltmeter. Okay. So, millivoltmeter inside it is inside the box. So, 2 probes are connected with the voltmeter and 2 probes are connected with the constant current source. So, now, so our aim is to measure the Hall voltage as a function of magnetic field. Then from the plot Hall voltage versus magnetic field, we will basically will find the slope, and from that slope you will get the Hall coefficient, okay, as I described in the theory class. So, this is one. So, I need magnetic field for this experiment. So, this is the electromagnet, we will use. So, here electromagnet as I described earlier. So, it has 2 coils, and it has pole. Here we are using flat pole, sometimes we use tapered pole. So, we have kept at particular air gap, and for that air gap, what is the magnetic field for different coil current, that calibration we have to do. So, we need Gauss meter. So, we have a Gauss meter here, okay, and this Gauss meter is along with the Hall probe. So, how to measure the magnetic field, that I have described in earlier classes. So, this probe will be used for measuring the magnetic field. So, I have to place at the middle where we will put sample, at that place I have to put in perpendicular position, gel in perpendicular position. So, in middle and perpendicular position, I think I have to take off, slightly off. So, I have put it here, it is in middle more or less, okay, or slightly I can make it, yes, it is more or less in middle, okay. So, now this is the constant current source, this is the constant current source for this electromagnet, for coil current, okay. So, these coils are connected to this power supply, constant current power supply, okay. So, so I think I will, if I keep it here, let me, so what we have to do, first we have to do calibration, okay. So, I will switch on, switch on the constant current power supply and the Gauss meter. So, here it is showing some value, it is showing some value. So, I have to keep in middle, okay, and make it perpendicular, because you know I have described. So, if this probe is not perpendicular to the magnetic field, if it is tilted, so you will not get the correct value. So, initially you have to adjust, 0 adjustment is there, make it 0. So, more or less it is 0, okay, more or less it is 0, okay. So, 0 current, 0 magnetic field. Now, we will increase the magnetic, we will increase the current, we will increase the current in step by step, okay, and magnetic field is here, you will get the magnetic field reading. So, you note down, okay. So, current versus magnetic field. So, for this current, what is the magnetic field? So, take in 0.25 or 0.3 or 0.2 step, and okay. So, note down. So, coil current and the corresponding magnetic field you can note down. So, this way you should take few datas, I think around 10 to 15 data you can take. So, I have maximum here, I can apply 4 ampere current. So, 4 ampere current, you see when I increase the current, so it change, magnetic field is out of range. So, I put multiplied by 1 and here multiplied by 10. That means, whatever here, so this here scale I have changed to the in multiple of 10, okay. So, it is a 1, so it is out of, so it is coming basically 4 digit in 4 digit. So, this here, so this will be basically multiply with 10 Gauss, okay. That means 6720 Gauss, okay. So, this way you can do the calibration of the electromagnet using the Gauss meters. So, after calibration, I know this, I will not use this Hall probe, okay. I will remove this Hall probe. So, now this Gauss meter I am not going to use. So, I will use only this power supply coil current. So, our measurement is now for a particular sample current, I will measure Hall voltage as a function of magnetic field, okay. So, this my sample, now I have to put in the, I will put this sample inside the one has to be careful inside the, I have to, I think, okay, let me check. So, slightly height I have to increase, slightly height I will increase, not this one, I will increase slightly height and I have to make it perpendicular. Okay. So, I will put inside the electromagnet, I will keep the sample in the middle, more or less it is in the middle now. Okay. It is in middle. Yes, it is in middle, more or less it is in middle. Okay. So, now sample is at the center of the pole piece. Okay. Now, I will apply magnetic field. I will apply magnetic field and measure the Hall voltage. Okay. So, this for zero magnetic field. Okay. What is the, so I have to first what I have to do. So, there should not be any confusion between this current and this current. This is for electromagnet current, we are telling coil current, and here for experiment I have to pass constant current through the sample. So, from here I am applying the constant current, I have to select Ix along the x direction. So, I will switch on this one. So, now at present current is 0, now milliampere current is 0. So, I will apply some current, say how much current I will put, say 3 milliampere, I am putting 3 milliampere. Okay. So, 3 milliampere constant current passing through the sample along the x direction. Now, along the y direction, what is the voltage, Hall voltage, that I will measure, because this already I have made that connection. Okay. Now, what is the voltage at 0 magnetic field? I will note down, this voltage is minus 61.9 or minus 62 millivolt. Okay. So, for 0 coil current corresponding 0 magnetic field, so this minus 62.0 millivolt, that is the Hall voltage. Now, I will change, I will keep this current constant. So, sometimes I should see I have put at 3, so it is more or less at 3, okay, at this constant sample current. Now, I will change the magnetic field, I will change the magnetic field, okay, and note down, you see it is the changing, minus 56.2 for this coil current, 0.36 corresponding magnetic field from the calibration curve you will find out. Okay. So, I am changing the magnetic field, then noting down the, okay, noting down the Hall voltage, it is a minus 51.3 millivolt at 0.7 7 ampere current corresponding magnetic field. Okay. So, this way you do the experiment. Okay. Change the magnetic field, go up to 4, 1 ampere. What is the value? Minus 0.47.1. Okay. So, this way you do the experiment. Okay. Now, for each data, again what we do, we just change the direction of the magnetic field or current, then you see Hall voltage will be just opposite. Just check it, just let me keep at one value, say 2, okay, 2 ampere current, corresponding magnetic field, coil current, and this sample current is fixed. Let me check it whether it is at constant or not. Yes, 3 more or less it is 3 milliampere. So, sometimes we have to check it is more or less constant, and for that this is the value. Now, let me change the direction of the, I think, direction of the magnetic field, then Hall voltage will be reversed. So, let me switch on this current, and check it, change the polarity of the magnetic field. I am applying in opposite direction. So, I have changed the polarity, okay. I have changed the polarity, and now magnetic field is 0. Now, I am applying this magnetic field. So, I should get the Hall voltage in opposite direction, but I am not getting. It is minus 96. I should get the Hall voltage in opposite direction. If I just 1 minute. Zero, this is 62, now it's 64, just slight change are there. Now it is minus 36. So, 66 opposite here basically, here, yes, it is opposite of course. So, at 0 magnetic field it was minus 62, okay, it was minus 62. Now, when I am increasing field, so it is decreasing, okay. So, for one direction of magnetic field it is becoming minus 36, it is minus 36. So, 66 opposite here basically, here. So, at 0 magnetic field it was minus 62, okay, it was minus 62. Now, when I am increasing field, so it is decreasing, okay. So, for one direction of magnetic field it is becoming minus 36, it is minus 36. So, 66 opposite here basically, here. So, at density in the metal it is increasing. So, that is a conductivity is increasing, resistivity decreasing, resistance decreasing. So, that is why in case of semiconductor we see that resistivity decreases with temperature, okay. So, that is the magneto-resistance, change of resistance or change of resistivity of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you. Of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the